Welcome to Module 6. In this module, we will discuss the product and quotient rules. These rules will expand the types of functions for which we can find derivatives. Let's start with the product rule. Given two functions u and v, the derivative of the product u times v is u prime v plus u v prime. Consider an example. The processing power P of x of a server measured in gigaflops is modeled as the product of the number of active processor cores, C of x, which equals x squared plus 3x, and the efficiency per core, E of x, which equals 2x plus 1 gigaflops per core. Here x represents the number of hours since the server was last rebooted. We want to calculate the rate of change of the server's processing power 4 hours after the reboot. Okay, so we know we've got the function c of x, which is given to us as x squared plus 3x. And we've got the function e of x, which we're told that this is equal to 2x plus 1. And now the processing power is the product of these two functions. So we have that the processing power, p of x, is equal to c of x times e of x, which equals to x squared plus 3x times 2x plus 1. Now, we could just multiply this out and we would end up with a polynomial, and from that polynomial we would be able to find the derivative using our standard rules that we've seen so far. But let's take a slightly different approach. How about if we call this first function here, we'll just call it u, and this second one here we'll call it v. And so we're finding the derivative of a product, u times v. And so we know that the derivative, well, let's write down the product rule. That would be u prime times v plus u times v prime. And so let's see, u prime. So we're going to take the derivative of what we're calling u here, and it looks to me like that's going to be 2x plus 3, and we're just using those rules that we covered before. And we're multiplying that by v, and v is just 2x plus 1. And we're adding that to u, which is x squared plus 3x. And we're multiplying that by v prime, and if v is 2x plus 1, then v prime here would just be 2. Now again, I could multiply all of this out and simplify it, but I'm asked in this problem to calculate the rate of change of the server's processing power 4 hours after the reboot. So we want to find p prime of 4. And so it's just as easy to put that in here as it would be into some simplified form. So let's just go ahead and do it. We get 2 times 4 plus 3 times 2 times 4 plus 1 plus 4 squared plus 3 times 4, and all of that times 2. And it looks like this first part here, let's see, 8 plus 3 gives me 11. 8 plus 1 gives me 9. Plus, let's see, here we have 16 plus 12, which will give me 28. And we're multiplying that by 2. And it looks like this whole thing just becomes 155. And so p prime of 4 equals 155. Next, consider the quotient rule. Given two functions u and v, the derivative of the quotient u over v is u prime times v minus u times v prime all over v squared. The efficiency E of x of a blockchain protocol is given by E of x equals x squared plus 64x to the negative 1 all over 3x plus 2, where x is the number of transactions processed per hour. We want to find the rate of change of efficiency when processing 8 transactions per hour. So I notice that I've got a quotient here, and I'm trying to find the rate of change of efficiency when processing 8 transactions per hour. So I need to find the derivative. I'm going to write down my u and my v here. This is in the form u over v, where u is equal to x squared plus 64x to the negative 1. And I know that when I do the quotient rule, it involves u, v, u prime, and v prime. So I'm just going to go ahead and write down u prime here. And it looks like I get 2x. Let's see, this negative 1 comes out in front, gives me a negative 64. I'm going to subtract the exponent by 1, so that's negative 64x to the negative 2. Now let's see, v, that would be my denominator here, which is 3x plus 2. And my v prime there would just be 3. Now, these are the values of u prime, v, and v prime for any general value of x. I'm interested in what's happening at exactly 8 transactions per hour when x equals 8. So let's go over here and let's find these values when x equals 8. So over here is where at x equals 8. And so it looks like I'm going to get u equals, this will be 8 squared plus 64 times 8 to the negative 1. And that turns out to be 72. U prime, let's see, that would be 2 times 8 minus 64 times 8 to the negative 2. You might note here that 8 to the negative 2 is the same thing as 1 over 8 squared, which is just 1 over 64. And looks like that's going to give me 15. V at x equals 8 is going to be 3 times 8 plus 2, which gives me 26. And v prime is just 3 no matter what the value of x is. Well, now I'm trying to find e prime of 8. So let's see, e prime of 8. This would be given by the quotient rule. U prime times v minus u times v prime over v squared. I'm just going to go ahead and plug those in. So u prime is 15. And I'm multiplying that by v, which is 26. Minus u, which is 72. And I'm multiplying that by v prime, which is 3. And all of that goes over v squared. So that goes over 26 squared. Well, we could just throw this in the calculator. Maybe we could do a little simplification. Looks like this turns out to be 174 over 26 squared. And I don't know what that is. I'm just going to plug it into the calculator, which is about 0.2574. Let's look at a few more examples. The productivity, P of t, of a low-code platform in terms of applications developed is modeled by P of t equals 2 times the square root of t plus 1 times the quantity 1.2t plus 1.5. This model is good for t less than 10, where t represents the number of months since the platform was adopted. We want to calculate the rate of change of productivity after t months. So we have a function, P of t, which represents the productivity of a low-code platform, and this is equal to the quantity 2 times the square root of t plus 1 times the quantity 1.2t plus 1.5. And what we want to do here is find the rate of change of productivity after t months. Well, that would just be the derivative of P of t. What I'm going to do here before we start trying to find that derivative is I'm going to rewrite this original function. I'm going to write this as 2 times t to the 1/2 plus 1, and that's times 1.2t plus 1.5. And that's just because t to the 1/2, I know how to find the derivative of that, whereas if it's written as the square root, then that's a little harder to find the derivative of. Okay, so let's see. We want to find p prime of t. And if I go over here and say, okay, I've got a product here, and let's call this part over here U, and we'll call this part over here V, then we know that the product rule tells us that P prime of T equals U prime times V plus U times V prime. So as long as we can find the derivatives of U and V, we should be able to find the derivative here of the entire function P of T. Well, okay, so we have U prime. So I've got this function here, I want to find the derivative of it. I've got 2 times t to the 1/2, that 1/2 would come out in front, and we would subtract 1 from the exponent. It looks like I would get t to the negative 1/2 when I do that. And I don't get anything from the 1 over here, because the derivative of a constant is just 0. So there's my U prime. Now V is just this function over here. It's 1.2 times t plus 1.5. Now I add that to U, which is 2t to the 1/2 plus 1. And now I'll multiply that by V prime. And if V is 1.2t plus 1.5, I can see that V prime would just be 1.2. Okay, well, let's see, I could probably simplify this a little bit. If I multiply this t to the negative 1/2 inside these parentheses right here, I would get 1.2. Now t to the negative 1/2 times t to the first would just give me t to the 1/2. And multiply this by 1.5, I get 1.5 t to the negative 1/2. And let's see over here, if I multiply 1.2 inside these parentheses, that's going to give me 2.4 t to the 1/2 plus 1.2. And let's see, it looks like I could do maybe a little bit of simplification here. I've got 1.2 t to the 1/2, and I've got 2.4 t to the 1/2, so if I combine those, I get 3.6 t to the 1/2 plus 1.5 t to the negative 1/2 plus 1.2. And now let's remember that the original function was only good when t was less than 10, which means that this derivative is also only good when t is less than 10. So we'll just write that down as well. The ratio of the number of bugs fixed, b of x, which equals 2x plus 1, to the number of maintenance hours, h of x, which equals x plus 6, measures maintenance efficiency. And here x is the number of weeks since the start of the maintenance period. We want to find the rate of change of this efficiency x weeks into maintenance. In this problem, we have the ratio of the number of bugs fixed given by b of x equals 2x plus 1. And that's being put over h of x, which equals x plus 6. So how about if we just call that something like maybe e of x? So we have this ratio b of x over h of x. And this equals 2x plus 1 over x plus 6. And we're asked to find the rate of change of this efficiency x weeks into maintenance. In other words, we want to find e prime of x. So if I start off by calling this first part up here, this top part, I'm just going to call that u, and this denominator here, v, then I see I just have to use the quotient rule here. So let's go ahead and write down the quotient rule. E prime of x is equal to u prime times v minus u times v prime, and all of that goes over v squared. So, okay, let's see. U prime, that would be the derivative of the top. It looks like u prime would just be 2. And that's being multiplied by v, which is just x plus 6. We're going to subtract u, which is 2x plus 1, times v prime, and if v equals x plus 6, then v prime will just be 1. And all of that goes over v squared. So that all goes over x plus 6 squared. Well, I believe we can simplify this a little bit. If we multiply the 2 inside the parentheses, we get 2x plus 12. And let's distribute this negative inside these parentheses here. And so that would be minus 2x minus 1. And all of that goes over x plus 6 quantity squared. Well, the 2x and the negative 2x cancel out. 12 minus 1 gives me 11 in the numerator. So it looks like our derivative would be 11 over x plus 6 quantity squared. The popularity index, f of x, for a programming language is modeled as f of x equals 100 over the quantity x squared plus x plus 20, where x represents the number of years since the language inception. We want to calculate the rate of change of the popularity index 5 years after the language's release. In this problem, we have a popularity index, f of x, for a programming language, and we know that x represents the number of years since the language's inception. We want to find the rate of change of the popularity index 5 years after the language's release. In other words, we want to find f prime of 5. So let's start by recognizing that we've got a quotient. And I will call the top part up here the numerator u, and I will call the denominator v. And so we see here that u is equal to 100, which implies that u prime is equal to 0, and v is equal to x squared plus x plus 20, which implies that v prime is equal to 2x plus 1. And we know that the quotient rule involves u, u prime, v, and v prime, so we can go ahead and write down the derivative using the quotient rule. F prime of x is equal to u prime times v minus u times v prime over v squared. U prime is 0, so this will be 0. That's multiplied by v. Honestly, it doesn't matter what it's multiplied by because it would still be 0, but let's just go ahead and put it in there. V is x squared plus x plus 20. Minus u, which is 100, times v prime, which is 2x plus 1. And all of that goes over v squared. So that goes over x squared plus x plus 20 quantity squared. What it looks like, this first part here is just 0. It looks like we just have negative 100 times 2x plus 1 in the numerator. And in the denominator, we have x squared plus x plus 20 quantity squared. So there's our derivative. Now remember, we want to find f prime of 5. So there may be some simplification or something I could do here to this derivative, but I'm going to plug 5 into it, so I'm not even going to worry about doing anything like that. F prime of 5 is equal to negative 100 times 2 times 5 plus 1. That's my numerator. And in the denominator, I have 5 squared plus 5 plus 20, all of that squared. Well, let's see. In the numerator, it looks like that's going to give me 2 times 5 is 10, plus 1 gives me 11. Multiply it by negative 100. That gives me a negative 1100. And down here we have 5 squared, which is 25. Add 5 to that gives me 30. 30 plus 20 gives me 50. So I have 50 squared in the denominator. And I'm just going to plug this right into the calculator. Looks like what we're going to get here is somewhere around negative 0.44. So the rate of change of the popularity index 5 years after the language's release is negative 0.44. In a server system, U of x represents the server load in terms of number of requests, and V of x represents the processing power in terms of operations per second. At a particular moment, the server load is 80 requests and is increasing at a rate of 10 requests per second. The processing power is 150 operations per second, but is decreasing at 5 operations per second. Find the rate of change of the total processing capacity, U of x times V of x, at this instant. In this problem, U of x represents the server load, and we're told here that at a particular moment the server load is 80 requests and it's increasing at a rate of 10 requests per second. And we can write that down mathematically. That means at some moment, and I'm just going to write, let's say, U of c. C just represents some number here. I'm not told what number that is, but it doesn't really matter. U of c, at that moment, I know that this value is 80. And I know it's increasing at a rate of 10. So U prime of c is equal to 10. Now also in this problem, V of x represents the processing power. And we're told that the processing power at this moment is 150 operations per second. So that sounds like we're told that V of c is 150, and it's decreasing at 5 operations per second. So that means that V prime of c is equal to -5. So we want to find the rate of change of the total processing capacity, U of x times V of x, at this moment. Well, U times V prime, we know that this is U prime times V plus U times V prime by the product rule. And we have these values of what's going on at this particular moment, so let's just plug those in. U prime is equal to 10, V is equal to 150, plus U, which is equal to 80, and V prime, which is equal to -5. Looks like that's going to give us 1,500. This will give us -400. Looks like our rate of change at this moment will be 1,100. In a data security system, U of x represents the number of encryption algorithms used, and V of x represents the total data volume in terabytes encrypted. At a particular point in time, there are 8 encryption algorithms, increasing at a rate of 2 algorithms per month. The total encrypted data volume at this moment is 15 terabytes, increasing by 1.5 terabytes per month. We want to find the rate of change of the algorithm to data volume ratio, U of x over V of x, at this moment. Here we have a data security system, and U of x represents the number of encryption algorithms used. Now we're told here that at a particular point in time, there are 8 encryption algorithms, increasing at a rate of 2 algorithms per month. So I'm going to write down U of c. Now c here is just some number that just represents the moment at which this is happening. So U of c is equal to 8, and we know that at that moment it's increasing at a rate of 2 algorithms per month. So know that U prime of c is equal to 2. Now we also know here that V of x represents the total data volume. And we know that at this moment, the total data volume is 15 terabytes, and it's increasing at a rate of 1.5 terabytes per month. So that means that at this moment c, V of c is equal to 15, and V prime of c is equal to 1.5. Now we want to find the rate of change of the algorithm to data volume ratio, which is U of x over V of x. Well, now this rate of change will be found using the quotient rule. We know that U over V prime is equal to U prime times V minus U times V prime, all divided by V squared. And so we'll just plug in our values here for U prime V, U V prime, and see what we get. Looks like what we have here is U prime, which is 2, times V, which is 15, minus U, which is 8, times V prime, which is 1.5, and all of that goes over V squared, so that would be 15 squared. Well, let's see. 2 times 5 will give us 30. 8 times 1.5 will give us 12, so we have 30 minus 12 in the numerator. 15 squared is 225. So it looks like we have 18 over 225. Oh, let's see, if we divide the top and bottom by 9, we get 2 over 25, and I believe that equals 0.08. And so we found the derivative at that moment. As we wrap up this module, I hope you've gained a solid understanding of the product and quotient rules. There is still one more major rule to go, the chain rule, which we'll cover in the next module. After that, we'll be ready to handle the derivative of just about any algebraic function that comes our way.